Mud is flying everywhere. The electric motors are screaming, and this bright yellow Rivian R1T punches through a deep water crossing like it's nothing. Then smash cut to a silent, spotless factory floor in the middle of Illinois where that same truck was born, in a building that cranks out an electric truck roughly every 3 minutes using liquid nitrogen chilled to minus 321 degrees Fahrenheit to literally shrink parts of its motors into place. And the wildest part, that futuristic factory sits in a town called Normal, Illinois. There is nothing normal about what happens inside this building. It's a 4.3 million square foot former Mitsubishi plant that Rivian has turned into one of the most advanced EV factories in the world, with another 1.1 million square feet being added just to build their next SUV, the R2. The same lines that build the R1T truck, the R1S SUV, and Amazon's electric delivery vans are being pushed toward a capacity of over 150,000 vehicles a year, with plans to get to about 215,000 once the new expansion is fully online. Every one of those vehicles starts its life as a flat coil of steel and ends as a fully tested, software-defined electric adventure machine. So in this video, we're going inside that plant step by step, from the Mitsubishi Ghost factory it used to be, to the massive steel presses, to the in-house battery lines, to the mind-bending liquid nitrogen motor assembly, and finally to the human-robot dance that bolts it all together and rolls it out the door. By the end, you'll not only understand how Rivian builds a truck every few minutes, you'll see why this one facility might be the blueprint for how American electric vehicles are made in the next decade. Before we drop into the factory, quick challenge for you. As you're watching, keep a mental tally of how many times you spot something that could only exist on an EV, not a gas truck. From skateboard chassis, to cooling plates, to battery modules, see if your guess matches what you think at the end. Now, let's rewind to the origin story, because this place wasn't always home to electric trucks and robots. If you walked into this building around 2015, you wouldn't have seen a single Rivian logo. For decades, this was a Mitsubishi plant, building gas cars in huge volume. When Mitsubishi pulled out, it left behind a 4.3 million square foot shell, stamping presses, assembly lines, paint booths, and a lot of dust. Rivian saw something different. Instead of starting from scratch on a greenfield site, they took over this massive existing factory in Normal, Illinois, and began the long process of ripping out what didn't work for EVs and rebuilding what did. That renovation was almost like doing surgery on a living creature. They had to reroute power, bring in high-voltage infrastructure for batteries and motors, and redesign entire flow paths inside the building so raw steel on one end eventually becomes a painted powered vehicle at the other. At the same time, the company was still relatively unknown. You had R.J. Scaringe, Rivian's founder and CEO, betting big that this old Mitsubishi shell could become the heart of a new kind of American car company. Thousands of local workers were hired and retrained, suppliers were brought closer, and gradually the Ghost factory started humming back to life with robots, welders, and battery assembly gear instead of combustion engines and exhaust systems. Fast forward a few years, and the plant now builds the R1T electric pickup, the R1S SUV, plus commercial delivery vans for Amazon, all riding on variations of Rivian's skateboard platform. In 2022, even while fighting supply chain chaos, Rivian built around 25,000 vehicles, and the Normal plant's designed capacity was set at about 150,000 vehicles a year, with expansion plans already underway. That expansion is not small. Rivian is adding roughly 1.1 million square feet to the site dedicated to R2 production, which will push the planned capacity up into the 215,000 units per year range once everything is up and running, with the R2 SUV scheduled to join the family in 2026. So picture this, a once-abandoned factory in a Midwestern town now re-engineered to push out cutting-edge electric trucks on a schedule that would have sounded impossible a decade ago. That's the stage. Now, how does a flat sheet of metal actually become an R1T body in a matter of minutes? Let's walk the line. We start in the stamping shop, which is basically the blacksmith of the entire factory. Only instead of a hammer and anvil, Rivian uses 6 gigantic hydraulic presses. Imagine coils of steel rolled into the plant like enormous silver toilet paper rolls. Those coils are unspooled, cut into blanks, and then fed into presses that can hit with thousands of tons of force. In just a fraction of a second, a flat sheet is slammed into shape as a hood, a door, a fender, or one of the massive body side panels that runs nearly the full length of the truck. Each part goes through multiple dies, one to do the rough draw, another to trim, another to pierce holes in windows, and often another to flange and refine edges. It's like watching origami at industrial scale, where every fold has to be within a fraction of a millimeter or nothing will line up later. Robots grab these newly formed panels and set them onto racks, where quality cameras and sensors check for tiny wrinkles, waves, or cracks. A bad press hit now would mean huge problems later in welding and final assembly, so this stage is all about precision under extreme force. But stamping isn't where the magic stops. The real transformation happens in the body shop, where hundreds of these parts are stitched together into a rigid safety shell. Here, orange and yellow robots swing around like mechanical dancers, each programmed to grab panels, position them, and weld them with incredible consistency. Rivian leans heavily on laser welding technology in this area. Instead of just traditional spot welds, high-powered laser beams run along seams, especially in areas where strength and rigidity are critical, such as around the passenger cabin and battery compartment. Laser welding brings a few big advantages. First, it's fast. A laser can zip down a seam in a continuous line instead of hitting hundreds of individual spots. Second, it's precise and clean, leaving less distortion and rework. You'll see lasers not just on body structures, but also later around certain parts of the battery packs where clean, repeatable welds are absolutely vital for sealing and structural integrity. Watching it in person feels like something out of a sci-fi movie. Bright blue light tracing along the joints while sparks flicker and robots move in perfect choreography. Right here, the first mini question for you. When you think about vehicle safety, do you picture software or steel? Because in a modern EV like this, both matter. That laser-welded skeleton is what gives the Rivian its crash structure. But the frame has also been designed around a massive battery pack that lives low and flat in the vehicle, which changes how energy is absorbed in a crash and how the vehicle handles on the road. Once the bare body is done, it heads through paint, sealing, and corrosion protection, critical but less visually dramatic steps. And then it's time to give this steel shell its heart, the battery pack. What makes Rivian different from many of its competitors is that they assemble their battery packs in-house, inside the same Normal, Illinois facility. That's a huge strategic move, because batteries aren't just another component. They're the most expensive and most performance-critical piece of the vehicle. In the battery area, think of long lines of sub-assemblies, modules, cooling plates, structural frames, electronics. The basic building block is the cell, individual battery cells provided by suppliers, and Rivian groups those into modules. Several modules then come together to form one big pack. Along the way, they integrate liquid cooling channels that snake between the cells, metal plates, and interfaces that allow coolant to remove heat during fast charging and high-power driving. One of the really clever steps you'd see in a tour is how the cooling plates and modules are pressed and sealed together. Machines use carefully controlled pressure, sometimes with air bladders or airbags inside fixtures, to make sure the thermal interface material spreads evenly between surfaces so heat transfers out efficiently. Too little pressure and you get air gaps. Too much, and you risk crushing cells or components. Rivian uses automated metering systems to dispense adhesive and thermal paste, then presses everything together under calibrated force so every pack behaves predictably at full power. Then you have structural bonding. The battery pack isn't just an energy tank. In Rivian's architecture, it's also a structural part of the skateboard platform. Adhesives, bolts, and welds turn the pack into a stressed member, which helps overall rigidity. Inside the pack housing, bus bars route serious current, and high-voltage contactors and safety electronics monitor every cell group. The final pack is sealed against the elements, tested for leaks, and electrically verified before it ever sees a vehicle. Here's where a subtle but important competitive angle comes in. By doing this in-house, Rivian can tune the pack design to each vehicle variant, R1T, R1S, and the delivery vans, and quickly iterate on thermal management, range, and performance without waiting on an external supplier's timeline. It's slower to set up at first, but long-term it gives them more control over cost and technology. Now imagine this. You've seen bodies taking shape in one corner, battery packs getting sealed up in another, and in the middle of the plant there's another critical line building the motors and drive units. This is where one of the wildest processes in the whole factory lives: liquid nitrogen motor assembly. Each Rivian drive unit has two main mechanical stars, the rotor and the shaft. The rotor is the spinning drum with magnets or magnet arrays inside. The shaft is the splined steel rod that actually transfers torque out to the wheels. Getting those two parts permanently bonded is not as simple as sliding one into the other and tightening a bolt. Instead, Rivian uses temperature to do the work for them. Here's the trick. Steel and other metals expand when heated and contract when cooled. Rivian takes the rotor shaft and plunges it into a bath of liquid nitrogen, bringing it down to about minus 321 degrees Fahrenheit. At that temperature, the steel shrinks slightly, enough that its outer diameter becomes just a tiny bit smaller. At the same time, the rotor drum is heated so that its inner diameter expands a little. Between those two temperature changes, you suddenly have a fit where the shaft can be pushed, or press fit, into the rotor with extreme precision. So in the motor assembly cell, you'd see the shaft coming out of an insulated enclosure, frosty from the liquid nitrogen, and the rotor warmed and waiting. Within a very narrow window of time, the shrunken shaft is lined up to the expanded rotor and pressed together by a powerful machine. Once mating is complete, the system just sits and waits while nature does the rest. As both parts return to room temperature, the shaft expands, the rotor contracts, and the interference fit between them becomes insanely tight, so tight that under normal operating conditions, they're not coming apart again. This is not just a party trick. That interference fit is crucial for reliability at high torque and high RPM. A sloppy connection would mean vibration, wear, or catastrophic failure over time. Using liquid nitrogen and heat gives Rivian precise, repeatable control over that connection. And because it's a purely mechanical bond, there's no need for additional fasteners or adhesives at that interface, which simplifies the geometry and helps balance. When you stand next to that line, you realize you're not just watching parts get assembled, you're watching physics being used as a tool, like an invisible clamp created by temperature. As those drive units are completed, other robots add inverters and gear sets, turning each motor into a sealed power unit ready to bolt onto the skateboard chassis. At this stage, things start coming together. The line where the skateboard is assembled brings the battery pack, motors, suspension components, and cooling systems onto one rolling platform. Think of it as the vehicle's spine, nervous system, and muscles all being snapped together. The chassis line has its own rhythm. Suspension subframes are loaded with control arms, dampers, and links, then mated to the main frame. The battery pack is lifted up from below by a massive fixture while the frame hovers above on a conveyor. In a synchronized motion, the two meet, and automated tooling bolts them together with the correct torque values on every fastener. High-voltage orange cables run from the pack to the drive units and inverters, linking the energy source to the motors. This is called the marriage station. The body comes in from above, the rolling chassis comes in from below, and a set of lifts and fixtures align them with millimeter accuracy. Then bolts shoot up from the bottom or in from the sides, locking the two halves into one structure. From that moment on, it looks like a Rivian, but it's still just a shell of plastic and metal on the inside. Final assembly is where the human-robot hybrid nature of the plant really shines. Robots help with heavy, repetitive tasks, lifting glass windshields and precisely placing them with adhesive, installing seats using big assist arms, or pushing dashboards into position. But so much of the cabin build is still human-driven. Workers route wiring harnesses through tight bulkheads, snap in interior panels, install air vents, screens, and door seals, and check panel gaps by eye and by feel. This part of the process feels strangely handcrafted for such a high-tech product. You might see a technician carefully aligning a trim piece, closing a door multiple times to get the latch feel just right, or running a fingertip along a seam to make sure it sits flush. Every stage feeds into a larger quality control network. If a sensor reads an out-of-range torque value, that station can flag the vehicle for inspection. It's easy to think of modern car factories as fully automated, but Rivian's normal plant is very intentionally a mix. Robots do the lifting, welding, and repetitive positioning. Humans do the refinement, decision-making, and high-consequence inspections. In a world where your truck can receive software updates over the air, the physical build still comes down to people who know what a good door slam sounds like, or what a properly seated weather strip feels like when it's tugged. Once a truck rolls off the end of the assembly line, the real testing begins. Every vehicle goes through a series of static checks first. Lights, screens, climate systems, power seats, and windows are cycled. Technicians plug into the onboard diagnostics to make sure there are no error codes from the power electronics, the battery pack, or the array of sensors around the vehicle. Think radar, cameras, ultrasonic sensors, everything that supports driver assistance and safety systems. Then comes the dynamic testing. Trucks are driven onto rolling road dynamometers, essentially treadmills for cars, where the motors are spun up under controlled load. This allows Rivian to confirm that each motor, inverter, and gearbox behaves correctly, that there's no unexpected vibration, and that regenerative braking works as intended. Brake stands test stopping performance, ABS, and stability control interventions. In some cases, water spray tunnels simulate rain to check for leaks, and rough road simulators shake the vehicle to reveal any rattles or loose connections. One of the underrated stages is software and calibration. Before a customer ever takes delivery, each truck gets the right software build flashed to its control units. For a long time, American car stories were mostly about Detroit and a few southern states. Now, one of the most advanced electric truck factories in the world is in central Illinois, inside a reused building that once symbolized the old gas-powered era. So the next time you see a Rivian R1T or R1S gliding past you silently, or you spot one of those Amazon vans rolling down your street, remember what's hidden behind that clean design. Somewhere in Normal, a coil of steel got slammed into shape by a press taller than a house. A swarm of robots welded its skeleton together with lasers. A massive battery pack was assembled in-house, its cells clamped under carefully calibrated pressure and wrapped in cooling channels. A motor shaft took a cryogenic bath at -321 degrees Fahrenheit so it could shrink just enough to slide inside a hot rotor and lock there forever as it warmed back up. Then hundreds of human hands guided it the rest of the way, routing cables, aligning panels, testing screens, listening for squeaks, and driving it on a rolling road to make sure everything works exactly as intended. All of that so the experience, when you finally press the accelerator on a muddy trail, feels effortless. That 3-minute build rate isn't a magic trick. It's the sum of thousands of hours of engineering, training, and iteration stacked on top of one another in a factory that was given a second life. If you've made it this far, you now know more about how a Rivian is built than most people who just see one on the highway. You've seen how a once-empty Mitsubishi plant became a high-volume EV hub, how steel becomes structure, how batteries and motors are assembled under extreme conditions, and how humans and robots split the workload to finish each truck. If you want to go even deeper into how modern EV factories work, from Tesla's gigapresses to battery gigafactories, let me know which plant you want us to tour next, and we'll break it down. And if you enjoyed this behind-the-scenes look inside Rivian's factory and want to see more videos like this, hit subscribe, turn on notifications so you don't miss the next factory deep dive, and drop a comment telling us which part of the build process surprised you the most.